right, so when we work with, I did a little extra work on this because this has been bothering me a little. And what I did is I think it might help. Are you scared of this? Are you scared? How many of you are scared of that strong induction? I knew it. I knew it. Somebody at third hour said, "Can we just be weak?" And I said, no, we can't be weak. So here, if this helps, just write this down. If P1, proposition 1, P isn't a variable, it's a proposition. Proposition with n equal to 1 is true. Okay. And, I'm going to put a little and here. If P of R is true for all R less than or equal to K. So let's break this down. Maybe you put it in a box. Okay? We need to have these two things happen. We need P1 and we need PR, where R is less than or equal to K. This is what we called step 1. This is what we called step 2. What else are we missing? The K plus 1 part. So for the strong, I'm going to continue here. It would be and proposition K plus 1 is true, then this is the old news. P of n is true for n greater than or equal to, what was that? Or n was an element of the positive integers. So I'm going to make another little box here. This was step 3. And for this one, we want P of K plus 1 to be true. So it's P of 1 is true. P of R is true when R is less than or equal to K. And then P of K plus 1 is true. So here's what we had trouble with third hour, and we're trying to unravel it a little bit. You're okay with proposition 1. We let n equal to 1, but we're trying to let go of the n stages here. We're just calling this proposition 1. This is proposition R. This is like by P of n equal to K. R is less than or equal to K. This is the strong format. What's saying here is R is equal to whatever you start with, 1, 2, 3, all the way to K. Those are what all those are. And then you have P of K plus 1. That's the next term you have to prove. So this is first term. This is my assumption statement, and we're expanding to include P of 1, P of 2, P of 3. Here, let's do it this way. This is P of 1, P of 2, P of 3, all the way up to P of what? K. See how this is a little stronger than just saying P of K? What's different? Before we just had this one and this one. Okay, but now what we're saying is these in-betweeners. We're not doing anything different, but we're saying that that's true. Yeah, awesome.
What's that symbol with the curve down the bottom right between the n and the
It should be an element of, yeah, so this should be, for P of n is true for n as an element of all the positive integers. Sorry about that. Okay, so let's hit this one more time. So the proposition 1, proposition R, where R is less than or equal to K. So we're setting up what R is, and then we're looking at the K step for that icky algebra step. So this is putting in the 1. This is just putting in R in for n, if you want to call it that. And then we're looking at P of K plus 1. And then we have to have the P of K plus 1 working for the formula and for adding the next term. And then you're saying that this is true for all n. Okay, so let's go And help me out so that I keep these letters straight, because that's what I had trouble with before.
So you'll need to prove for P, for R is equal to 1, 2, 3, and K, right? Not just.
Great. So now let's look at number 2. So we're going to restate what they have. They said P of n, okay, is that. All right. So B1 equals B2 equals 1. That's given. And Bn equals 2Bn minus 1 plus Bn minus 2 for n greater than or equal to 3. Okay, that's what we're starting with. Now we do proposition 1. If we put in, we want to see what B of 1 is. Actually, we're not going to do B of 1. What are we going to do? B of 3? Because we're going to go 2B of 1 plus B of 2. And that should be equal to B3. And we remember the Fibonacci sequence. It's going to be 1, 1, then what? 2, 3, 5, and so on. Okay? This would be Fibonacci 1, Fibonacci 2, Fibonacci 3. Okay? So using this formula, Fibonacci 3, and we'll just call it Fibonacci 3, 2 times Fibonacci 3, 2 Fibonacci 1, Fibonacci 2. So, and we're trying to say that they're odd. Now, this is kind of a strange one here. Prove that B of n is odd for all of these. So we're trying to show that these are all odd. So let's just do it easier here. Is B1 odd? Is f of 1 odd? Yeah, 1 is odd, so that's good. How about f of 2? That's going to be odd as well. All right? So if you look at this one, f of 3 is 2 times this odd, which is f2, or f1, plus f2, which is odd. Are these going to be, is f3 going to be odd? Well,
I don't think that it's good enough. It goes 1, 1, 3, 5.
1, 1. Oh. Oh, shoot. Yeah, that's right. Well, those are the Fibonacci numbers, but if we list this sequence here, let's do this with the formula. We're going to get B, there we go, B3 is 2, B2, B1, whoop, had it right before. So many letters, B1 plus B2. And then is 2 times,
2B2 plus 1B1.
yeah, that's right. I was right. So 2 times 1 plus 1, which is 3, is that odd? Yes, it is odd. So proposition 1 passes. Next one, proposition, now we're going to assume that B of R is odd for all R less than or equal to K. Then B of R is odd for what values of R?
1, 2, 3,
I like it, except aren't we supposed to start with 3?
for all of the equation.
Oh, but it's still R is equal to 1, 2, 3, all the way to K. So that's kind of that middle, that's the strong step that you're least comfortable with. Look at what we did. We're looking at B of R instead of BK is odd. That's the given. and then we're just saying 4r is equal to those. So that's kind of easy. br instead of bk, br is going to use all these up to k. We're going to use 1, 2, 3 all the way up to k. And now all you have to do is the p of p. Yeah, p of n plus 1. That's the one we're going to do next. This is your p of n. This is your p of n plus 1. And so now what we're going to do is b of k plus 1 is going to be equal to something. So I got a little hint for you. We're going to do, above here in green, I'm going to write this formula. B of k equals 2b of, let's see, k minus 1 plus b of k minus 2. What will b of k plus 1 is going to go here? What will be here? 2bk, yeah, b of k. K minus 1. And then this is going to be plus b of k, add 1, what do you get? Minus 1. So all I did is I upped the values in the sequence by 1. All right. Now, is bk always odd? In the assumption, it is. How about the one before it? Is that going to be odd? Yes. So if this is odd and this is odd, but this is 2 times an odd, what's 2 times an odd going to be? Plus an odd, what are you going to end up with? Odd. So b of k plus 1 is also going to be odd. So now we can do our final statement. Okay. Therefore, since P1 is true and R is equal to K plus 1 for, I'm going to write this out, R is equal to 1, 2, 3, dot, 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 all the way up to K, then P of n is true for all n greater than, or n an element of z.